to the 6th Developer of the Year Michael Wormit Award. My name is Shirin Farati. I am a professor of theoretical and computational chemistry at the University of Groningen, the Netherlands, and I will be chairing this award ceremony. About 6 years ago, on March 14 of 2015, the life of Michael Wormit was cut short. It was and still is a tragic loss for all of us. Michael was a husband, a son, a friend, a great colleague, and a mentor. He was also part of QChem developer community. We gather here today to remember Michael and to celebrate his accomplishments and his contribution to our community. His life was short, but he left a mark, and his work will continue to make an impact. And this is something we should cherish and remember. To always remember Michael's contribution to QChem community, QChem's board of directors established an award in his name. On behalf of board of directors, let me introduce Michael Wormit Award. The award has been established in August 2015 to recognize excellence in developing new methods and algorithms in the area of electronic structure and implementing these methods in a state-of-the-art computer codes within QChem Open Teamware Community Project. The award is given annually and includes a certificate and $500 prize. By this award, Michael is remembered for developing a state-of-the-art algorithms and computer codes for many body electronic structure methods and for his leadership in community building, educating and mentoring junior team members, and software infrastructure developments. Any member of the QChem developer community is eligible for this award. The selection criteria are scientific innovation, excellence in code development, contribution to the infrastructure and developers community. Nomination materials should be sent to office qchem@qchem.com with the subject Wormit Award nomination by January 15th of each year. The first award was given in San Diego in March 2016 to Evgeny Epifanovsky, 2017 to Andrew Gilbert, 2018 to Alec White, 2019 to Junho Lee, and to Pavel Pochilko and Yuji Mao in 2020. Today's 6th Michael Wormit Developer of the Year Award will be presented. We have received several outstanding nominations. The board appointed an international selection committee. The committee has chosen Dr. Marta Lopez Vidal as the recipient of the 6th Michael Wormit Award. Please join me virtually in thanking Marta for her contribution to the company and to the community and congratulate her on being selected as a recipient of 2021 Developers of the Year Michael Wormit Award. On the side note, that makes me personally very proud, Marta is the first girl to receive this recognition, and I do hope this inspires more female developers in the future. Marta received her Bachelor in Chemistry from University of Barcelona, Spain in 2015. After that, she received her master's degree within a prestige program of European Master in Theoretical Chemistry and Computational Modeling, Erasmus Mundus TCCM. And after that, very well equipped with a theory background, in 2017, she joined the group of Professor Sonia Coriani at Technical University of Denmark to carry out her PhD research on extending equation of motion coupled cluster methods. The nomination of Marta was mainly based on her PhD work at Professor Coriani's group that includes implementation of frozen core valence separated equation of motion coupled cluster framework for X-ray spectroscopy. The selection committee specifically cites the development of the tools for computing time-resolved transient state X-ray absorption and transient state X-ray photoelectron spectra, two very important spectroscopy techniques. Marta not only develops QChem for her own projects, but also helps QChem community in fixing bugs and teaches junior group members how to code into QChem. A short note from the nomination letter. First, Marta is the top of 5% of graduate students in our field. And second quote, I'm deeply convinced she has all the qualities for a successful scientific career if she decides to choose that path. And I do hope that you do, Marta. Marta is currently doing her postdoc at the University of Cardiff, UK with Professor Peter Knowles. And today she's going to talk about development and application of coupled cluster method for X-ray spectroscopy. And before that, this is a digital version of the certificate signed by Anna Krylov, the president of the QChem company. And you will receive a printed and a framed version of that at your address. So now the floor is yours, and we are very looking forward to hear about your exciting development and results. I need to make you a presenter.
Okay, can you see my screen?
Yes, I can see your screen.
Great. So thanks a lot for the introduction. And well, I'm really honored to receive the prize. And I'm really thankful to the QChem community and also my supervisor at DTU. And so, yeah, as I said, I'll be talking about mainly the work I've been doing during my PhD within QChem. So it's about the development of coupled cluster methods for X-ray spectroscopy. And I'll also try to show some of the applications. Okay, so here is the outline that I'll be following. I'll start with a brief general introduction. I'll give an overview of the theory after that, and then I'll show you some of the results I've obtained during my PhD. And well, that will lead us to the conclusions. So let's start with the introduction. So I very much like this analogy that so medical doctors, they use X-ray to scan patients if they want to see inside their body, if they want to see their structure inside their body. So it's the same idea we can use X-ray for in molecules. So with X-ray, we can also see inside the molecules. So in this case, at least what I've been doing during my PhD is mainly understanding the electronic structure of molecules using X-ray. And so from here we can better understand molecules and their properties and eventually their reactivity. And so I'm pretty sure you all know that X-ray radiation is just light, but it's in the higher energy region. So because if it's in the higher energy region, when it will interact with atoms and molecules, it will also interact with the higher energy electrons. So those that are closer to the nuclei. And these, we call them core electrons. And the typical interactions that will happen is that either the electron will absorb this X-ray photon and get excited, or if the energy is above the ionization threshold, so it will get ionized. And so during my PhD, mainly the talk would be focusing on two different spectroscopy techniques. And so the first one is X-ray absorption spectroscopy, so that exploits the excitation of electrons. And the second one is called X-ray photoelectron spectroscopy, that instead exploits the ionization of the electrons. And so then we can further classify X-ray spectroscopies depending on the kind of electrons we're looking at, depending on the kind of core electrons. So for instance, if we're looking at the first shell, starting from the nuclei, so then we call this KH. If it's the second one, it's LH, the third MH, and so on. And so today I'll be mainly focusing on KH and LH. And so the motivation to do theory about X-ray, so to develop new X-ray methods, is that in the last few years, so there has been a lot of development in the experimental side, and so that led to the construction, for instance, of the Maxford synchrotron in Sweden. Or another example is the European X-ray electron laser that opened in 2017 only. And so these three facilities allow experimentalists to do very new kind of experiments that weren't even possible years ago. But the problem is that they're so complicated, that gets so messy that you can actually not really understand it without the theory. So this development on the experimental side really needs to go hand by hand with the theory to really, so we can really understand what is it that's actually going on. And so with that, I'll review the theory I've been using. So we want to simulate spectrum. So basically we need the intensity in function of the photon energy. And so as I said, so X-ray will interact with the core electrons. And so in X-rays they will get excited, and in X-rays they will get ionized. So basically what we need is the energy of the final state and the initial state and the probability of this to happen. And so for this, we will solve the electronic Schrödinger equation. And this is the electronic Hamiltonian. And the method I've been using during my PhD is coupled cluster theory. So in coupled cluster, the wave function is given by this equation. So where psi naught is phi naught, sorry, it's a determinant, a single stator determinant that we typically take as Hartree-Fock. And so then we can recover this missing correlation in Hartree-Fock by using this, what we call an exponential ansatz, and that this will lead to an expansion that by allowing the modification of one electron at a time, 2 electrons at a time, and up to n electrons at a time, then it will allow to recover this correlation. In practice, of course, it's unfeasible to go up to n electrons, so we typically need to truncate it. And the approach I've used mainly during my PhD is coupled cluster singles and doubles, so we truncate atom doubles. And so another very extended approximation is called frozen core CCSV. And so then it's basically that we only allow the valence electrons to be modified. And of course, it's also one that I've been using during my PhD. So here now we have the coupled cluster wave function that we need. So we need to solve the coupled cluster equation. So this is the energy equation and then the amplitudes equations. So we can get the energy of the ground state and the wave function. So now that we have the ground state, we need to also describe the final state. And this we can do using the equation of motion coupled cluster. So, and in this method, in EOM, the wave function is given by this expression. So instead of an exponential parameterization as we had before, here we have a linear one. So this is the R operator. And so it can take different forms if what we want is to describe excited states. So basically it will excite one electron, but it can also describe ionized states, for instance, and it basically just ionizes one electron instead. And so then we need to solve the equations. In this case, this equation, so that will give us the difference in energy between the excited states and the initial states. And then the intensity we can get by calculating the reduced density matrices. So this is for XAS. Then from here we can calculate the electric dipole moment, and then will give us the oscillator strength that will give us the intensity. And in XPS, we can also use these density matrices, and we can just approximate them like this. Okay, so if we solve these equations, we can get the full spectrum like this. But so, as I've said before, so we are actually only interested in this region over here, which is the high energy region. Actually, we don't want to describe all these other states. And actually, the algorithm we use, so first it starts solving the lowest excited states. So it will be very unpractical to have to solve all these states first to arrive the ones that we are really interested in, the X-ray region. So that would be inefficient. And then, well, there are some methods that can directly tackle this region. But so then the problem, if you're still taking into account the valence space, then you can have some convergence issues, because so we say that actually this region is embedded in a sea of valence states that will hinder convergence for the X-ray states. But so to solve these problems, we can use what we call the core valence separation. So that it basically states that we can decouple core and valence spaces because there are big difference in energy. So basically, it reduces in EOM. So we need to restrict this R operator we saw before, so that it acts only on the core region. And so, for instance, here you can see a graphical representation of CDS. So here we would have the full space of singles and doubles. And so in CDS, we would retain only the excitations that involve at least one core electron. So the ones here in red represented with a capital N. And so like this, we can directly solve the equations, so we get already as the lower states the X-ray states. And also like this, we get rid of all these valence states that will otherwise hinder convergence. Okay, so that was the theory, and so now I can start showing you some of the results, see how the method performs. So I'll start with ground state spectra. So here I'm showing you the XAS of adenine, the molecule here on the top right corner. And so on the left, I'm showing you the carbon KH, and on the right, the nitrogen KH. And so the red spectra are the theoretical one, and the black one is the experimental one. So as you can see, we can reproduce experiment quite well. But so it's of course not only about reproducing it, but also understanding it. And so this we can do, for example, using natural transition orbitals, because so these are a visual way to represent excited states in terms of orbitals. And so, for instance, here we can, where we see only one peak in the spectrum, in the experimental spectrum, we can see that actually it involves 3 different excitations that are represented here by NTOs. So we can also simulate XPS. So here I'm showing you the spectra for the same molecule, adenine, and same carbon and nitrogen edges. And as you can see, we also get to put a green, and then we can also visualize these ionized states in this case. And this, instead of using natural transition orbitals, we use Dyson orbitals. So basically, they represent where the electron has been ionized from. Okay, so far it was ground state spectra, so we're starting from the ground state. And now I'll move on to excited state spectra, which is what we call time resolved experiments. And so they're called time resolved experiments because they happen in 2 steps. So in the first steps, we pump our molecule in the UV visible region, so we excite from the valence space. And then in the second step, what we want to do is probe this already excited state using X-ray. So we're gonna either excite or ionize, as before, XAES and XPS, but this time the time resolved counterparts. And so these experiments are quite appealing because with this we can understand these processes where, for instance, so here this is a typical case that actually I'll be also showing you in the following. So we have the ground state that we excite with UV, and then when it relaxes, it can take different paths. It can relax back to the ground state or jump to a dark state and pi star. And these processes are very important to understand if we want to study, for instance, photochemical reactions. So the idea here is that we can probe with X-ray what state we have populated. And so here I'll show you an example of this. So here we decided to study uracil 2 towards valence excited states. And so here the first one is an n-pi star, which is a dark one. And the S2 pi star is the first bright excited state. So here, if we, so first, I'm showing you here, so red is the ground state. In the experiment, we have only the ground state. And so then we have only a signal here from the S2. So this is the first bright excited state. So for instance, if we're trying to probe these states at the carbon KH, and so we could do so because we would get intensity only from this state and not the dark one as one. And if instead we're looking at the oxygen edge, we get the opposite case. So in this case, we get intensity almost only from the dark excited state. So this would be a way to probe which one do we have. And so that was using XAES, but we could also do that for XPS. And so here I'm showing you the same molecule, uracil, but in this case, so it's ionization instead. And we could also prove the S1, so the dark and pi star state at the oxygen edge, as we get intensity in the different region. Okay, so what I've shown you so far, it's been only KH spectroscopy, but so now I'm also gonna show you LH spectroscopy. But this is actually a bit more difficult to represent because we need to include relativistic effects. So let's look at the relativistic effects in chemistry. So first we have scalar relativistic effects and also spin orbit coupling. So let's start with the scalar relativistic effects. So these are due to the fact that the speed of light is finite. And so the problem is that core electrons, because they're very close to the nuclei, they can get very high energies close to the speed of light. And so then is when relativistic effects can arise, and then they get higher relativistic mass. And so that makes them compact to the nuclei. So for instance, in practice, what happens is we have these contractions of the orbitals S and P, and instead we will have an indirect expansion of orbitals DNF. But so these are maybe not so so important if we only want a qualitative spectrum, because so at the end it's just a shift in energy. So let's look at spin-orbit coupling. So spin-orbit coupling is due to the fact that we have charged particles in relative motion, and that induce magnetic field. And then is when we can see this spin-orbit interaction. So that will lead to mixing of states of different multiplicity, for instance, singlets and triplets, and also splitting of orbitals PDNF. So in the following, I'm gonna show you the case of 2p. So the 2p, for instance, in a non-relativistic world, they would be degenerate, but because of spin-orbit coupling, we have this splitting. And so we have 1 2p 1/2 and 2 that we go to 2. And this will actually have a big impact in the spectra, as you will see. So to take this into account, what we decided to use, it was a perturbative approach. So in the first step, we solved equations for the non-relativistic Hamiltonian, and this we do by, as I've shown you before. So we just use the method of the regular non-relativistic method, and then in a second step, we add this spin-orbit correction. And this we'll do using the bright Pauli Hamiltonian that I'm showing you here. Yeah, I don't need to go through this. So let's look at LHXPS. And so these are the non-relativistic results of the first step, where, so as you can recognize, the non-relativistic p orbitals, and then we get this spectrum in red that completely fails in reproducing the experimental spectrum, as you can see. But so this is why we need to correct it with spin-orbit coupling, so that we do by constructing the spin-orbit Hamiltonian, diagonalizing, and then we get the new spin-orbit basis. So we get a new states, and this is how our Dyson orbitals look after this transformation. And so if we want to reproduce the spectrum, we do the same with the intensities, we transform them. And so now you can see this blue curve is with a spin orbit correction that reproduces well these two peaks with 1 to intensity. Okay, so that was for XPS. So the same we can do with XAS. So the idea is the same. So in this case, in the first step, we use the excitation energies ion, and in the second one, so the same, we use the bright Pauli Hamiltonian. We diagonalize and we get the new basis, and so we need to correct for the oscillator strands, and then we get the spectrum. That, as you can see, we get also a good agreement with the experiment, and we can really reproduce this splitting of the p orbitals with 2 on one side and 1 on the other. And so before finishing, I'd like you to show maybe a more applicative case. And so it's the benzene cation here. So it was a couple of years ago that some experimentalists had recorded this spectrum, and they were quite excited because they were getting this splitting in this peak, that they thought it was due to Jean-Taylor effect. And so they asked us if we could just prove it. So let's first go back to the parent species, to benzene neutral, and so to understand what is the Jean-Taylor effect in the benzene cation. So for this, here I'm showing you the molecular orbitals of benzene, and we need to focus in particular in the top ones, so the HOMO. And so, because of course, if we're going to ionize an electron from benzene, we're going to ionize from either B2G or B3G, which are the highest in energy. So if we ionize from B to G, it will of course go up in energy. And actually what happens in the benzene molecule is that it gets compressed. Whereas if we ionize from B3G, it will elongate. And so this distortion in the geometry due to a loss of degeneracy in the orbitals, this is the Gentero effect. And so we thought that's going to be very easy. We just need to calculate the spectrum for one and the other, and we're going to see that the two peak so much, and that's the end of the story. But of course, it's never as easy. And so we started doing some calculations, and actually, so the numbers didn't match. It was, well, actually, that was a problem, that they matched too well. So they were right on top of each other. So these two peaks couldn't really come from one or the other structure. And actually, by doing some more calculations and reading a bit the literature, so we found out that actually, so you cannot really think about the benzene molecule as only the benzene cation as either one or the other, because actually it fluctuates from one molecule to the other. So you have both at the same time. And so what was this peak? So after doing some more calculations, so we found out that actually, so of course the first peak is, we only have one, and that's very well reproduced. And so this is, so this in the first peak is just to fill in the SOMA, the single orbital that was ionized. But if we want to go higher in energy, so the problem is now that we have an unpaired electron in the valence space that can couple, the spin of this electron can couple with the ones that we're going to excite. And so this is actually the reason of this splitting. So this is a clear example that experiment cannot go alone, that they really need a theoretical spectrum to understand what is actually going on. And so with that, I'll just conclude. I'm going to start just briefly summarizing. So the frozen core valence separation equation of motion CCSD method allows to study different core-related processes, such as the ground state spectroscopy, within X-ray absorption spectroscopy, X-photoelectron spectroscopy, and then we can also describe excited state spectroscopy, so simulate these time resolved experiments. And that now the inclusion of spin orbit allows us to also simulate LH spectroscopy. And so just a brief outlook. So this also, so all these methods are available in QChem. And so it also sets the basis to study for the correlated processes. Some, for instance, other spectroscopy techniques like X-ray emission and resonant elastic X-ray spectroscopy that actually they're already implemented in QChem. But then we could also go to simulate other edges, other systems, or include other effects. And so with that, I would like to thank all the people that made that possible, especially like to thank QChem, my supervisor, that helped me during all these 3 years, and of course her group, you for all the support. And then I would also like to thank Professor Anna Kriller, who introduced me to QChem, and we've been working together ever since. And also some people from her group, especially Dr. Fahilko and Xintian Peng, and again Itipanovsky from QChem, that helped me a lot at the beginning, introducing me to the QChem community, but they've also been helping me all these years. And yeah, with that, I would also like to thank you all for your attention.
Thank you very much, Marta, for this very clear talk. And I would like to ask people to type their question in the question box here or the poll. Okay. I will read the question for you. Does the theory needs to be modified to calculate time resolve XAS/XPS? What does it mean to put regular equation of motion, excitation energy, couple cluster, single doubles in front of the FCCVS calculation when specifying the method?
Yeah, so to calculate this time resolved experiment, so what you need is basically the excited state. So you need the, if we focus into XAS, for instance. So we will need the valence excited state and the core excited state. So what you need to do is calculate both in the same calculation and then couple these excited states, both valence, the one you want to excite from, to the core ones that is going to go. And so like this, well, of course, you get the energy directly just by taking the energy difference, and then you can get the oscillator strengths from this coupling. And so the idea is the same with XPS. You just calculate first your valence excited state, and then your core ionized state, and then you can also just couple. Of course, it depends on what excited state you're interested in. That you might want to go beyond CCSD, because if you need some more, if you wanna to describe well these excited states that are different by more than one electron, then you really need to include more excitations to catch this correlation.
Okay, there is another question. What reference state do you use to model TR XPS or TR XAS states? I think by TR they mean triplet. I don't know.
Time resolved, I guess.
Okay, TR, yes.
Okay.
Which references do you use to model them?
Yeah, so actually it depends. You can use different reference states, but I think the one that we've most commonly used, you can use just like the singlet reference state, yeah, so it's the same depending on which ones you want to describe. So you might want to choose another one. So for instance, we've also tried starting with a triplet state instead, because then you can catch up some of the like you can access some excited state that you couldn't with the singlet. Then you can like for instance, if you wanna do time resolve from the singlet directly, that you could also do, and then you don't need to couple the excited states, but then you might hit some convergence problems. So then you might want to use some maximum overlap method or something like this. But my experience has been mainly either with the singlet or the triplet.
Okay. So there is another compliment. Great talk, Marta. Which spectroscopy do you think is the best? Do you have a favorite one and why?
A favorite what, sir?
Which spectroscopy do you think is the best? Do you have a favorite one and why?
Well, I guess these time resolve spectroscopies are pretty exciting because it tells you a lot of not only the molecule in the ground state, but also the valence excited states and how it relaxes into other ones, and which path it will be following. So I think this is very exciting, and it also yeah, gives you a step ahead in the theory. So
okay. There is another one. Great talk, Marta. Congratulations on the award. Just curious, what is the atomic size of the molecule for which the FC, CVS, EOM, CCST calculations are feasible computationally speaking?
Yeah.
The size of the molecule.
So, well, of course, it depends on how many resources you have and how much time you have. But I mean, I've never gone very far. I think the farthest I've been doing, it was like adenine, for instance, and so I mean, you can get quite these in one day or something like this.
Okay. Another one is which structures do you use for the excited state calculations?
So the ones I've used, it's always been using equation of motion.
I think, yeah, but okay. Let me check. Yeah, these are the, I'm sure that people can always contact you when they have more questions.
Sure.
I have one general question out of a curiosity. What is the project of your postdoc about?
Yeah, so actually it's still within couple cluster and equation of motion, but so now what we want to look at is we want to go beyond the Born-Oppenheimer approximation, and so because it gets too complicated to first solve the electron Schrödinger equation for Born-Oppenheimer and then going back, because then you have all these potential energy surfaces that are coupling to each other. So the idea with the project is to forget about the Born-Oppenheimer approximation and just treat electrons in the same footing as vibrations. And so the idea is actually to build a new general framework where you would treat systems with bosons coupled to electrons, and like this you can describe any kind of system like this. So you can imagine you can also describe, for instance, actually we're starting with this, so describing electrons coupled to photons, for instance. So yeah, that's the idea.
Very nice. So I don't see further questions. I hope that I didn't miss any, because this is a very small screen here I have. Apparently not. Oh, there is another one. Okay, there is one. Could you elaborate why it makes a difference if the reference for TRXAS is a singlet or triplet? As far as I understand, after the X-ray interaction, the whole system is again in singlet.
So, well, what I meant is that so it depends on what you want to describe as an excited state, and so depending on the reference you have, so it will be easier to access from one configuration or another. So sometimes if you have only a singlet, you cannot go from there with only one excitation to all the excited states you're interested in. And so as I also said, this is not well described when you have double excitations with CCSD, because you miss most of the relaxation effects. So in this case, you might want to choose another reference state that can access the ones you're interested in. I don't know if I answered the question. I hope so.
Okay. Yes, I don't see any further question. And with that, I would like to thank you again for taking the time and effort for doing all this exciting development inside QChem. And
well,
also,
it was my pleasure.
Yes, and also being here today. And I wish you best of luck. QChem actually wishes you best of luck for future, and I hope that you stay active in our community with all this exciting direction that you are exploring. And as the nomination letter said, I hope to have you as a future colleague in the community as well.
Well, thanks a lot. As I said, it was my pleasure to both work with QChem with all the developers. It's a very exciting community, and of course also giving the talk. So thank you for giving me this opportunity.
It was all pleasure. And with that, I will close this session, and please feel free to contact Marta if you have any question regarding the, because it's up and running, all implemented in QChem. So please contact her for any type of exciting science you would like to do with these methods. With that, I would like to thank everyone who took the time to be here. In Europe, it's quite late, and also you, Marta. And I hope to see many of you in the next webinar.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.